Hello, everyone. I think it's always tiring to speak for the last presentation. And yeah, we had quite a lot of interesting sessions. So I hope to keep it a bit more fun, relaxing, not too much of technical depth. So I'm going to talk about requirement traceability in Xen functional safety with OpenFastTrace. So in the last presentation, I stressed upon the fact that what all things we need to do as a part of the Xen functional safety. So one of the things was to write the requirements, and there is still a missing puzzle to it. That is, how do we start to link the requirements to the code, to the tests? Because without linking, there is a possibility that it will go obsolete in some days. So we need a way by which from a test, you could exactly trace it all the way back to the market requirement or to the first level of requirement. So my name is Ayan, and I'm working on the Xen functional safety. And this presentation I'll be giving with Sebastian, who is working in Exasol, and he is the maintainer and the co-founder of the tool called OpenFastTrace. So it's a kind of a hybrid presentation that I'll be giving. So the first thing that when we started writing the requirements, the first thing that came to our mind was it should be pretty lightweight in the sense that we do like writing the code. We don't particularly like to write, for example, doc or some proprietary format. So we wanted to write it in a way that is very similar to the code, which anyone can use, reuse, review, and use it anywhere. So that was one thing. The other thing was we still wanted to use Git for the revision control, so we don't want to use some other thing. So we basically wanted to decouple the requirements, what is being written as the code, from the traceability tool itself, in the sense that the tool shouldn't really tell me how to write the requirements, or it shouldn't really force me to keep the requirements in a specific format. In the sense that if tomorrow, if someone wants to use a different kind of a tool, it should be very easy to extract the requirements out and then import it or put it in a different tool. It can be a proprietary tool, or it can be some other open source tool. So on this criteria, why did we choose OpenFastTrace? So it basically allows us to write requirements as code. It's open source. It is least intrusive, that it really doesn't define how you write the requirements, in the sense that there are only a few keywords that it requires in order to do in order to generate the traceability report. So beyond that, it's all like how you write the code, anything. And the best thing that we liked about the OpenFastTrace was it allows versioning of each requirement. So in the sense that there is a possibility that a requirement can be updated in the future, and you need a way by which the tool can tell you that, hey, take a look at the downstream requirements. If you have updated, let's say, a L2 requirement, take a look at the L3 requirement. So there should be a way by which the tool should be able to prompt you. Otherwise, it's very easy for someone to update and then kind of forget about the downstream parts, and then it may break up the thing, the consistency. And it should be able to link requirements. That is, these are text files. It should be able to link text to text, text to code, and code to code. And actually, thanks to Mikkel, who found out or analyzed the OpenFastTrace, and it was due to the research he did that we were able to come up with such a good tool. And the other thing is, this is one of the few, I would say, requirement traceability tool which has been actively maintained. So it was started somewhere in 2015, 2016 time. And there has been consistent releases, and there has been a good community behind the tool, to maintain the tool, to update the tool. We will tell you that there were some features that we specifically at Xen Functional Safety wanted to introduce as changes, and those were quite quickly addressed, and there is a good bug report for that. And last but not the least, we wanted a tool which should absolutely generate the report in least amount of time, because ultimately all this thing what we are writing, it is going to scale up to huge number of requirements, tests, test codes. It may be in tens of thousands. So we definitely wanted to have a tool which can generate the report, let's say, in less than a second, and the tool does that actually. So now, when I have described a bit about the OpenFastTrace, let's learn a bit more about the tool from the person who had authored the tool himself. So I'll play a recording from Sebastian.
Hello everyone at the Xen Summit. My name is Sebastian Bär. I'm co-founder of the free software project OpenFastTrace. I'm happy for the opportunity to speak to you via video today. I will give you a quick overview about what OpenFastTrace is and what it can be used for. Ayan from AMD will hold the second part of the talk and explain how OFT is used for functional safety in the Xen project. To underline the importance of requirements tracing, let me take you back to 1996, the year of the maiden flight of the European Space Agency's first Ariane 5 launcher and its catastrophic loss. 40 seconds after launch, it self-destructed as a consequence of an error in the inertial reference system. The error sprung from a small detail, a piece of code from the older Ariane 4 that wasn't properly adapted to the new rocket. Not only this, the sad punchline is that the code should not even have existed anymore, since the quick recovery from late hold in the start process, which this code was designed for, was no longer a valid mission scenario. This mistake was estimated to have cost approximately $370 million. As we discuss the capabilities of OpenFastTrace in tracing requirements and avoiding such oversights, please remember this story. Effective requirement tracing can safeguard our projects, ensuring that every line of code serves a relevant purpose. Errors that tracing catches fall largely into one of three categories. Forgotten requirements mean unplanned extra work that strains your budget and prolongs your time to market. Stuff that no one ordered is complete waste of time and money. And obsolete features are the worst of all, since you spend your time maintaining nothing but dead weight without even realizing it. What they all have in common is that they lead to wasteful complexity, eating away at your time budget and reliability, which in turn means increased maintenance effort. This will impact both customer satisfaction and team satisfaction. Let's take a quick look at how OFT came to be. It all started at a German software company called Dreisoft, which later would become part of the Finnish Electrobit group and even later Continental. OFT was not the first requirement tracing suite that had its roots there. In fact, the first ancestor was the requirement manager, which saw the light of day in 2003. In 2004, the next generation added multi-level tracing required in the context of the AUTOSAR operating system. There was a parallel development with T-Rex, which did unfortunately not see widespread use. And since both were not fast enough, they spawned Allosaurus. And yes, our projects at that time were in full pun mode. While undeniably a lot faster, Allosaurus was less user-friendly. And thus, finally, we decided we needed to go open source and apply what we learned from the previous projects. So in the end of 2015, the OFT project was born. We had the first full-featured version available mid-2018. Later that year, version 2 brought the first breaking change with an improved but unfortunately not fully backward-compatible API. There have been many releases since then, with major versions requiring newer Java versions, like version 3 with Java 11 in 2020 and version 4 with Java 17 in 2024. OFT does its job on two levels. It offers a way to write requirements that removes all the unnecessary fuss around the process and focuses on the content. And when you are done with writing your requirements, it lets you trace them into your product. In a nutshell, you can separate requirement tracing into four main tasks. Authoring, which is the process of writing requirements and annotating code. Splitting the requirement chain along the lines of responsibilities. Tracing from your part of the work to the ones above to see if you got everything covered. and then tracing the chain all the way down from the top to the bottom, verifying that it's intact. We are first going to take a look at the authoring part of requirements engineering. In the context of OFT, authoring means both writing specification documents and annotating codes to document which requirements it covers. Here's how a typical OFT document looks. It is either Markdown or restructured text, with embedded requirements in a compatible format that OFT can extract from the text. Both formats are so simple that everyone can learn them in 5 minutes, and they are guaranteed to be still readable in 50 years from now. A specification item in OFT starts with an optional section title, followed by a unique ID, description, rationale, comments, and other fields. The ID is the only mandatory field. The ID starts with an artifact type, a freeform tag that indicates the level in the requirement hierarchy. Then you have the requirement name, or if you prefer that, a number. The last part is the revision number, used to help detect semantic changes at a later point in time. We also see here that a specification item can cover another one. In this case, a high-level requirement REQ details a feature FEAT, and it can mandate coverage in one or more artifact types. In our case, a design. Here's how a tracing chain works. At the top of the example, we have a feature specified in Markdown. The second line is the specification item ID, which is used to refer to all other nodes in the chain. Let's take a look at the matching user requirement. The one new thing here is the cover section, which, you guessed it, is responsible for creating links by referring to the ID of the covered item. The chain can be as long or short as you like. Artifact types are not hard-coded. If you need a new one, just use it. We skipped discussing the design here, since there's nothing new from a tracing perspective. At the bottom of the chain, we usually find tests and implementation. These use special tags embedded in comments to link to the covered item. We already established that you write specifications in OFT as simple text files and treat them like code in your projects. So, what could be more logical than using your IDE to speed up the authoring process? The OFT project provides templates for popular IDEs that prepare parts of the requirement description, depending on the artifact type, and guides you through writing the content. In the example shown here, you can jump from one field to the next with the tab key. Notice also how the required coverage is pre-filled with typical values and how we change the unit test into an integration test. Next up, we talk about how to distribute work in a team. Software projects are rarely a one-developer show, and the people involved often have distinct roles and responsibilities, which means that they should be able to focus on their part of the work while still being able to collaborate. Of course, OFT supports this kind of cooperative workflow. How long your requirement chain needs to be depends on the complexity of your project, the involved teams and roles, and personal preferences. For most projects, the OFT team worked on 3 layers were sufficient. System requirements, which is the user's view, design, the software maker's plan, and code annotations, the software maker's actual product. You can either exchange the original documents between the teams, so for example Markdown, or use the XML-based exchange format. As you can see on this slide, depending on the role, the people produce different documents with different artifact types. The product owner, for example, is responsible for the system requirement specification, which typically contains features, user requirements, business risks, or budget constraints. The architect, on the other hand, writes design specifications, and in those you find design decisions, structure, behavior, technical risks, and technical constraints. The developer writes the code with the implementation and the test, and if you want to, you can even trace into the test results. Remember that you're free to decide how many layers of documents you want, and of course which artifact types should appear in them. As we discussed, if you treat everything like code, even your specifications, then you can use the same tool chains and processes that are so successful in the programming world. A typical workflow looks like this. The users want ARM support, so the product owner branches off the system requirements to work that request in. First, there's a draft commit. Then there's a second commit that fixes the review findings. Once everyone is happy, the document is merged back to the main branch and gets a tag. Next, the product owner informs the architect that a new release of the system requirements is available, and the architect sets out to work that in. Once the architect tagged and released the design, it's now the developer's turn. And again, the same steps are being followed. Tracing one level up tells you whether you covered everything that you or your team got as input requirements. If so, your job is pretty much done. In OFT, you simply restrict the artifact types to the ones on your level and the level above. Run a trace command and then fill the gaps until the report is green. As you can see, only the artifact types we filtered for appear in this particular report. In the snippet of the report, we see here two specification items, one that's covered properly and one that isn't. The defect one is missing coverage by a design item due to the covering item being outdated. If you wondered what the revision number is for in the specification item IDs, this is your answer. To detect a semantic change in a requirement was not worked into the covering item. It's the most frequent requirement engineering oversight that happens in non-trivial projects. It's also one that is notoriously hard to spot without tool support. For quick day-to-day work, we have a console version. This is ideal for the gritty debugging work in case you broke a link somewhere. The HTML report looks nice and is very accessible. This is also what you would hand to decision makers. They like slick documents, progress bars and check marks and just enough detail to have a good idea what's going on. It otherwise, of course, contains the exact same information as the console version. The final step is tracing all documents, including code, together to see if everything in the project is properly covered. Again, you can either feed the original documents or the OFT exchange format into this overall trace. OFT follows the Unix philosophy. Do one thing, do it well. Use files for data exchange. Allow chaining tools to solve more complex problems. So you can use a find command to collect all relevant documents from a file system and pipe the list into OFT to produce a trace over all of them. And OFT is indeed fast. The command line above traces all sub-projects of OpenFastTrace within less than half a second, including rendering and storing the HTML report. Let me show you several improvements that we have added to OpenFastTrace in collaboration with the Xen functional safety team. Previously, specification items were derived from code tags with automatic generated names and fixed revision numbers of 0. This was done under the assumption that users would only require tests and implementation from design items. Therefore, these specification items, being the last in the chain, didn't need further distinction. The Xen team presented a unique use case where tracing was required from implementation code to test code, something we hadn't accounted for before. To make this possible, we first added control over the revision number of the specification items defined by code tags. Add a revision number in the tag for the target artifact, and OFT will use that number in the generated ID. Next, we did the same thing for the specification item names. Now we have complete control over how the item IDs created from tags look. We also added an importer for reStructuredText, something our Python users have been waiting for quite a while now. That means that you can now write specifications in RST. Last but not least, PDF generation and printing is now more comfortable, since you can add a command line parameter to expand all sections in the HTML tracing report. If you found interesting what you saw, I invite you to visit our project on GitHub and try out OFT. You find us under github.com/itsallcode/OpenFastTrace. Thank you for your attention, and don't forget your requirements. Who knows, maybe that will save you $370 million one day.
So now that we have learned about why OFT is being used for the Xen functional safety project and what OFT is, I think the last part of the question is how we are actually using the OFT to do the traceability. So let's take a look at that. So apologies for the font, it's quite small. Can I see it? Where is it going? Okay, I can't see it. Oh, okay, now I see it, yeah. So this is where we start, the market requirement. So here what we do is that we specify, this is the ID that we specify here. And this is the ID that OFT uses for the tracing. So each specification ID consists of 3 types. That is the artifact type, the name, and the revision. So artifact type, we call it as the Xen MRQ. Again, you can call whatever you want, and then you have the name and you have the revision number. Now, the important thing is that this whole thing needs to be unique in the sense that this shouldn't be repeated anywhere else in any of the other requirements or the code or anywhere. So this is how it tracks it. And since we have, we say this is tilde1 in the sense that ever since the requirement was created, it has never been changed. So that's why the revision number is tilde1. And this is the description, rational needs. So what the needs tells you is that this requirement also needs, or it has a downstream link to a product requirement, and and the artifact type of the product requirement is the Xen PRQ thing. So the same thing here. The only difference is the artifact type is the Xen PRQ in the case of product requirement, and what it does is that it uses the covers keyword to say that which market requirement or which upstream requirement it is linked to, or it covers. So it says here that it is covering these two requirements, and subsequently this also needs a further artifact type to cover it, and that is called as Xen SSR, which is the artifact of the L3 requirement. And this is how we have the software safety requirement. So the same things. One of the reasons we wanted to use RST was because it renders quite well. So we really have a nice way to export it into a doc or a PDF format. And so what you would see here is that we are trying to say that it covers this product requirement, emulated timer, and it requires a Xen validation test case. So Xen validation test case is the artifact type of the validation test case to which this requirement is linked to. So further down, we have the test case, we have the test code, and we have the test job. The difference between the two is the test case actually describes how the test, how the test is to be implemented. So, for example, if someone who wants to see, what all are the prerequisites for the test, what should be the environment, what is it testing, what are the error conditions, which was one of the questions. So, all these details can be found in this test case, and it says that what all things a test case covers. It covers these two requirements. And from there on, this is where we have, until here we have all the text files or the RST files, and from there on we have the code files. So this is like a C code, and this is like the YAML code. So this is the test code, and this is the test job. It's a bit difficult to read this, but it actually says that it is trying to cover this particular test case, and it needs a test job as its dependent. So this is how the traceability report looks like. And sorry for this, this weird looking. It was quite large to fit it in a screen. So it actually tells you that what all are the things that you have covered. So if you see here Xen MRQ and you see all of them are crosses, that means they are missing some of the downstream links. But you see that some of these, they have the ticks here, like console IO hypercall, emulated timer, emulated UART. It means that you have all the subsequent nodes in the chain, like Xen SSR, validation test case, code, and job, all of them linked to this product requirement. But there might be something more that this needs, so that's the reason why the parent still has the crosses. And to understand how the traceability report looks like, so this is the unique specification ID of this. And this is where it gets linked to the to the level 2 or to the underlying requirement. And here, if you see, it says here that needs Xen SSR, but there is no link. So we can see here that the corresponding downstream node is missing. So that's the reason it gets a cross here, and then it also the parent also gets a it's marked as cross. That's incomplete. And then you have the same, so you have a validation test case, a test code, and a test job. And you see in the same way, like you have it, you have this as the downstream element, which says, so in is basically the downstream, out is basically the upstream. So this covers the SSR. This is the test code, this is the test code, and this is the test job. And this doesn't have any further downstream link. So all of this is covered. And because this chain is complete, so you see a tick here, you see a tick here, you see a tick here. Inevitably, you'll always see a tick here because there is no downstream link. As long as it is linked to the correct upstream, there will be a thing. So one good thing that I like is that, for example, if someone goes and modifies the test code, maybe adds some error conditions or something in the test case, let's say, because we forgot to capture some of them. So we will update this as 2. And then immediately there will be like a cross showing that it's broken because it is still linked to ~1. So that's how the tool actually tells us that, hey, take a look at the lower nodes of the chain. And yeah, this is how we have used the OpenFastTrace. So in a nutshell, it was quite a simple, usable, and a very, very neat kind of a tool which we wanted to use just for tracing the requirements, and I think it fulfills our needs. So thank you all, and I'm ready to take any questions that you have.
It wasn't really clear. Is there a link between the actual code and these requirements? The comments in the code? How does that work?
Yes. So if I show you this one. So do you see this one? There is a comment in the code. So we have put the comments there, and that is how it gets linked from the requirement or from any RST file to the code.
But this is the implementation of the test.
Yes. Yeah, please.
How does it handle changes in the code and test in this case regarding updates to specification requirements? For example, if somebody submits a patch that changes some code, updates the test to match the new code, but the old test would not match the new code anymore. How does it detect its need to be verified with the requirements?
Yeah, I think that's a good question. So basically what the question is that if there is a change in the code, okay, sorry. If there is a change in the code, then does it tell you that you also need to take a look at the requirement or the requirement needs to be reviewed? Unfortunately, the tool doesn't do that. It works the other way around. So if there is a change in the down elements in the code, so that is going to, so for example, if there is a change in the requirement, the tool is going to tell you to look at the code since the code is dependent on the requirement, but not the other way around. So that's a limitation. Any other questions?
How does it detect changes in that semantic version? So it says you need to bump to the semantic version of the requirement every time you make significant changes, but let's say you forget. Is there some way to go to the Git history and say when you forgot to change the version numbers?
So is there a way for the tool to check the Git history and say that the requirement has been changed, but the revision number hasn't been changed? That's the question, right? Yeah. No, the tool isn't that capable to look at the Git history and see whether the requirement has changed. So it all depends upon, like it's like a policy that we have, like you need to update the number, but the tool doesn't. So if you forget to update the number and you have updated the code or the requirement, anything, basically the tool will still assume that it's still the old one in terms of tracing. Yeah.
Should we call it review, I guess? It's review, like the reviewer should catch that. Right?
Yes. Yeah. I think that's all that we have for the time. So, yeah. Thank you.